Hello guys, welcome to today's class where we'll be looking at another aspect of binary operations. In this aspect, we'll be looking at operation properties on tables. Now, the operation properties that we'll be dealing with are operation properties that actually will be dealing with two variables or two objects. If you remember, from closure property, we can deal with what? More than one object, we can deal with two objects. We usually deal with either two or less than two. For associativity, we deal with three objects. So because we deal with three objects or three variables in associativity, we tend not to use the operational tables to actually express them. Okay, so for commutativity uses just two variables. So we'll be expressing that also on the tables. And then also, of course, we have our identity elements and then our inverse elements. So we'll be expressing how we can actually solve binary operation questions using these operational tables. So we'll be explaining how these operational tables actually work and then how we can actually work with them. We are taking an example here. We have an example one here that says construct the operation tables and state if they are closed under the given operations. So we are given a certain set of which we are asked to actually construct the operation using our basic operations. We have plus, we have times, we have times. That's the addition and the multiplication. That is what we'll be using in this case. For the Roman figure 1 here, we have a set. You have a set here. We want to construct a table containing 1, 2, 3, and 4 with the operation plus. So what we'll be doing is to test if they are closed under the given operation. So under this operation plus, we want to see if they are actually closed. So how do we create the tables? Because we have 1, 2, 3, 4, we create them on a vertical and also on an horizontal axis. We have 1, 2, 3, 4. The same goes there. 1, 2, 3, 4. And then we close our column. We know the operation we're using here is a basic operation, simply addition. Now, so the first thing we do, since we know how to do this, now we'll be relating them based on where they intersect. We'll be looking at this one, looking at 1 here. 1 and 1 intersect at this point. That means 1 plus 1 here, giving us 2. 2 plus 1 intersect at this point, giving us 3. 1 and 3 intersect here, giving us 4. The next one, 1 and 4, gives us 5. That is, adding both of them. The next one we have 2 plus 1 here, giving us 3. 2 plus 2, giving us 4. 2 plus 3 giving us 5. 2 plus 4 giving us 6. The same thing goes here for the next one. We keep on adding the ones on the vertical with the ones on the horizontal. So from here we say 3 here plus 1 here giving us 4. The same 3 plus 2 giving us 5. 3 plus 3 giving us 6. 3 plus 4 giving us 7. We have 4 plus 1 giving us 5. 4 plus 2 giving us 6. 4 plus 3 giving us 7. And 4 plus 4 giving us 8. Now that we have this, we are now asked to determine if the values we have, if it is closed under the operation addition. Now, this is the set. The set that we have here contains just 1, 2, 3, and 4. And then we see that in the table that we formed, we are having non-members of the set, that is non-elements of the set like 5, 6, 7, and 8. And these are not members of the set that we're considering. So because they are not members of this set, we therefore say that the operation is not closed. See what? The operation, since 5, 6, 7, and 8 are not elements of the set, whatever we call it. We can call this set A. Are not elements of set A, then the operation is not closed under set A. So that is the operation here. Once you can see that there are some elements that are in this particular table that are not in the original set, then it implies that this operation is not closed under this set A. We'll be looking at the second example. The second example here, we have -2, 0, and 2 are the elements of the set with the multiplication operation. Okay, let's name this set B. We have containing -2, 0, 2. with the multiplication operation. The very first thing we need to do is to create our table, knowing that we have just 3 elements. We have minus 2 times minus 2 here. Since we know it's the multiplication operation, we can start multiplying each of them. Minus 2 times minus 2 gives us 4. Minus 2 times 0 gives us 0. Minus 2 times 2 gives us minus 4. Moving on, we have 0 times minus 2 giving us 0. 0 times 0, 0. 0 times 2, 0. Move on to the next one. We have 2 times minus 2 giving us minus 4. 2 times 0 giving us 0. 2 times 2 giving us 4. So these are the elements that we have here. We have an excess of 4 and minus 4, which are not elements set B. Hence, I can say the operation is also not closed. It's not closed under set B. So we're looking at the third example here. The third example, we have a set containing minus 1 and 1, 1 and minus 1, with the operation multiplication. So we know that when we have the third one here, we can name this set set C. So we have 1 and minus 1 with the operation multiplication. Creating our table here, we put our two values on the horizontal, on both the horizontal and vertical axis. So we have a multiplication. We have 1 and minus 1. We have 1 and minus 1. So multiplying here, we have 1 times 1, 1. 1 times minus 1, minus 1. Minus 1 times 1 giving us minus 1. And then minus 1 times minus 1, that is this times this, giving us 1. If you look at this, you realize that all the elements here that have been formed are what? 1, we have minus 1, we have minus 1, we have 1. They are all elements that are contained in the set C. So since all the elements here, which are 1 and minus 1, are all elements of set C, hence the operation, this operation is closed under set C. So this is what happens when we actually use our knowledge of this to actually apply the knowledge of closure properties of our binary operation properties on operational table. Next class, we'll be looking at another question where we'll be analyzing the commutative property and also the closure property using the operational tables. See you next class.